A common misconception I've come across is that EVs can't be tuned or there's nothing to tune there. You just have the power that you have. And it turns out nothing could be further from the truth. So in this video, I'm going to walk you through a bit of how I've approached tuning on this EV conversion and how that might be applied to production EVs.
This the home-built electric 1940 Chevrolet of Paul Mangelsdorf.
This is the greatest EV to ever run Drag Week.
I do want to start off with a couple caveats. First, this video is going to be based on the Open Inverter Project method of inverter control developed by Johannes Hübner. There are other ways of controlling inverters and other ways of going about it, but this is the way that I am familiar with, and so that's what I'm going to talk about. Second, for my Open Inverter friends, this isn't really going to be a video on how to tune your EV conversion using Open Inverter. For those, I suggest you go watch Johannes or Damian McGuire's videos. They actually understand it at a much better level because they built it. Third, I'm not an electrical engineer, so I'm sure there are going to be some small details or quibbles that actual electrical engineers have, and I'm sure that they will tell me about them. And finally, this is going to focus on AC EVs. Yes, there are DC EVs, especially older ones and older conversions, but the industry has moved to AC power primarily because you can tune them much more easily. It's important to understand that in a modern EV, you have your battery, which is supplying DC power, and your motor, which is an alternating current motor. In between the two is an inverter, and that inverter is taking the DC battery power and creating AC power, typically three-phase AC power for the motor. What's critical is that it's not producing a steady state AC power like you might find coming from the grid, where it's at a fixed frequency and the amplitude changes based on your demand. That inverter is actually manipulating the AC power that it sends the motor in order to control it. When we look at an electric motor, we have the rotor, which is the part that rotates in the middle of the motor, and the stator, which surrounds it and has windings from each of those three phases. The inverter can manipulate the AC wave that it is sending to each phase to adjust where the magnetic field is. But we're actually talking about multiple magnetic fields. So in a common application, we'll have three pole pairs. Or basically think about it like we have three bar magnets with a north and a south, and a north and a south, and a north and a south. And so the inverter is creating multiple magnetic fields, and it needs to be able to control where that magnetic field is relative to the rotor. To zoom in a little more on one of them, let's imagine we're looking just at this upper part of the motor. We've got the stator out here with its windings, and we've got the inside of the rotor, and let's say that one pole of the rotor is here, and the magnetic field is generating another pole here. So this is running down to the center of the motor, and this angle here between the magnetic field and the rotor, we'll call it theta, is the slip angle. And so that's going to be something we're going to talk about in the parameters in a minute, but the inverter is going to control that slip angle to control how much force it's applying to the rotor. It's also going to control the strength of that magnetic field, which is also going to be a part of how much force is applied to the rotor. Now, how is it doing all of that? Well, this is one of three phases from a Tesla large drive unit. This would have been in a Model S or X rear-wheel drive car. On this end, it's receiving DC power from the battery, all three phases are, and then on this end, it is outputting to one of the phases of the motor. In through here are the switching electronics. In this case, they're using isolated gate bipolar transistors, or IGBTs. And down here are the gate drivers. They're actually controlling those gates. And basically, those switching electronics and that phase of the inverter is acting like this, a single pole double throw switch. And so it can be sending positive battery voltage or negative battery voltage or no voltage at all. And so many, many times a second, it is switching through those three positions to create the AC wave on that phase. The inverter's getting input from a few things. First, the accelerator pedal that's telling it how much power and speed do I want. And second, from an encoder on one end of the motor. Just like a crankshaft position sensor or a camshaft position sensor, this wheel uses the teeth on it and this sensor that gets mounted into the end plate to tell the inverter where the rotor is and how fast it's spinning and in what direction. The inverter takes that information and then, using the parameters that we've provided it and the algorithm built into the firmware, it decides where to place the magnetic field and how strong it should be to get the response that we want out of the motor. So now we're going to take a look at the parameters that I control on this car and talk about how they impact the tune of this inverter. This is the control panel for the inverter in my EV conversion. Coming down here to the parameters, this is where we're actually doing some tuning. I'm going to come back to the motor parameters in a minute, but these are the bulk of the parameters we're going to change. We do have some parameters like these in the inverter that are basically set them and forget them. This tells the inverter sort of how those switches are set up, how various sensors are set up. This is telling it how the throttle is set up and some parameters in how we ramp that throttle in. This we do some tuning with that there. And also what is the sort of some minimums and maximums here, how we're approaching the control. And then some controls here for regenerative braking. When does that kick in? How strong does it kick in? Does it turn the brake light on? And then your derating. Basically, these are at various temperatures and currents. When do we start turning the power down? Coming back up here to the motor parameters, some of these, like pole pairs, remember in that drawing I was showing you a 3-pole pair motor, this one is a 2. Some of these and how the encoder is set up, things like that, maximum frequency, those are all fixed. However, it's these up here that we're really manipulating the tune with. We'll come back to boost in a minute, but starting with field weakening frequency. We found lowering this, we are able to get more launch off the line, though we lose a little on the top end. As I've lowered this in the car, I've had a better ET, but the same mile an hour in the quarter mile. That really applies to these here, the maximum slip, or minimum slip, but the maximum slip applies until we reach the field weakening frequency. Above the field weakening frequency, we're increasing slip until we reach the F constant. Once we reach that, we're then using this maximum slip value. So we're basically creating a slip curve with these parameters, much like you might think about a timing curve in an internal combustion motor. There are a few others here that you may be curious about because they have interesting names like boost or field weakening start. This basically allows us to give a little bit extra power when we are just starting to turn the motor because it needs to overcome that inertia. And so this amplifies the power when we're at low throttle, low speeds. And similarly, we found, especially on these Tesla motors, that tends to trip a safety on the inverter that it doesn't need to trip. And by raising the field weakening frequency, we can avoid that. So when we're just starting low throttle, low speeds, we use this field weakening frequency, but at full throttle, we'll use this one. So that's the basic idea of what we're tuning. We're using which frequencies are the field weakening and the constant, and then we're applying a slip value below the field weakening and above the field weakening, and then ramping in between them. At least with the Open Inverter project, a lot of figuring out the amplitude that is being applied is being done by the algorithm of the inverter. But we have to set those parameters around the slip and how much we're applying, when we're applying it, And like I mentioned, there's a lot of adjustment there, even though it's only a few parameters. One interesting example coming from this car is that the F-Slip Max for below field weakening is very different on this car than on a very similar car that runs the same motor and the same battery packs, but has different weight distribution, different aerodynamics, different throttle ramping, and they're able to run a much higher value there than I am. I am hitting some of the inverter safeties that they are not, and that is limiting my power off the line. So finding ways to manipulate all that and the best fit for the car takes a lot of time, same as it would in an internal combustion car. So the last question might be, how does this apply to production cars? And that has been a tricky question to answer. Cars like Tesla's are fairly locked down, but there are a few manufacturers, particularly a company or two out of Canada, that have figured out how to get in there and increase the power limits that their inverters are pulling. Sometimes they're taking advantage of things that Tesla has built in for their own use into those motors, and sometimes they're developing their own. When it comes to production EVs from other companies, it's really a new frontier. We're going to have to do a lot of data logging. We're going to have to figure out what the basic low voltage wiring harness looks like so that we can start figuring out, can we get into those computers and control them in the same way that somebody like HP tuners can get in and control the computers in an internal combustion engine? Or are we going to have to go with full replacement boards? For example, the Tesla drive unit that's in my EV conversion behind me uses a replacement, basically brain board. It leaves the gate drivers from Tesla in there, but it replaces all the control electronics because it's so difficult to get into Tesla's electronics. Other EV conversions emulate the rest of the car, but then they're stuck with the tunes that Tesla developed. And so as we get into more performance EVs on the road from major manufacturers, we're going to have to figure out, are we just getting in and playing in their sandbox, or are we going to have to change the whole control system to do what we want it to do? Fortunately, I think there is a lot of information that is transferable from the side of the community that is trying to figure out how to hack and control EV components for use in conversions. And I think a lot of that information is going to be helpful in how do we approach getting access to and tuning production EVs. It's all a brave new world, but it is one that I'm excited about. I guess at the end of the day, my message here is that it is possible to tune EVs. It is more than just telling it to use more power. And it's not the end of the world. We're still going to have a need for tuners and dynos and playing around and tracks with EVs. I've done a ton of tuning, both at the track and on closed parking lots with my EV conversion, and I expect that I'll do a lot of the same with production EVs as well. At the end of the day, I think that hot rodding is more about an attitude than a fuel type. And so I encourage you to keep an open mind, and if you're interested in more of this, check out the Open Inverter community. There's a lot of great information there on how to control EV components and use them in applications they were never intended to. And I hope you'll stick around to see some more of my adventures and have some of your own.